Now, in this lecture, we find out the distance between the centers of two circles. In the drawing, we have rectangle ABCD. Note that side AB of this rectangle is equal to 7 units in its length. And side BC equals to 24 units in its length. Inside this rectangle, we have those two circles. The center of this circle is here at point Q, the center of this circle is here at point P. Our mission is to find out the distance between the centers of those two circles, that is to say the length of this line segment QP. So first of all, because of the fact that ABCD is a rectangle, it means that all those four angles are right angles. So I'll write it down. This angle equals to 90 degrees. This angle also equals to 90 degrees in its size. This angle equals to 90 degrees. And finally, this angle must be also equal to 90 degrees in its size. In addition, we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC. But AB is 7, therefore DC must be also equal to 7 units in its length. Likewise, according to the sum rule, side BC equals to side AD. But BC is 24, therefore AD must be also equal to 24 units in its length. In the next step, we'll focus on the right triangle ABC, and we'll implement on this right triangle ABC the Pythagoras theorem. So in the right triangle ABC, by PT is a dimension for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse on the right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and it must be equal to AB square plus BC square. Repeat again, according to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. So AC square, that is the square of the hypotenuse, equals to AB square. AB is 7, therefore AB square is 7 square, that is 49, plus BC square. BC is 24, therefore BC square is 24 square, that is 576. So we actually found out that AC square in total equals to 49 plus 576, that is 625. AC square equals to 625. We take out all of this equation and we get that AC equals to the square root of 625, that is actually 25. So we actually found out that the length of the hypotenuse of the right triangle ABC is equals to 25 units. AC equals to 25 units in its length. So, the right triangle ABC blocks the circle, and the right triangle ADC blocks the circle. So, in the next step, we will develop a general formula for the radius of any circle that is blocked by a right triangle. Triangle ABC is a right triangle. The right triangle ABC blocks this circle. According to our definition, the radius of this circle is x. So we'll find out the value of x only by knowing the side lengths of this right triangle ABC that blocks this circle. Okay, so we define the point of tendency of tangent BC with this circle as M. OM is the radius of this circle that is equal to x. The radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. I remind it to you that according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Point O is the radius, is the center of the circle. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, rule number 1. Okay. In the next step, we define the point of tendency of tangent AB with this circle as N. We join points O and N together by straight line. ON is the radius of this circle that is equal to x. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So inside this quadrilateral NOBM, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside the quadrilateral NOBM we have 4 right angles, therefore can relate to this quadrilateral is a rectangle. And you also know that the opposite sides of a rectangle are equal to each other, that is to say NO equals to BM, but NO is x, therefore BM must be also equal to x. Likewise, according to the sum rule, in rectangle NOBM, side OM equals to side NB, but OM is x, therefore NB must be also equal to x. So we actually found out that quadrilateral NOBM is not a rectangle but a square. Why? Because all of its sides are equal to each other, each side is equal to x. What is the length of this line segment AN? From the drawing it is very easy to see that AN equals to AB minus NB. Again, AB minus NB equals to AN. So AN equals to AB, that is A, minus NB, that is X. So in total, AN equals to A minus X. AN equals to A minus X. What is the length of this line segment CM? From the drawing it is very easy to see that CM equals to CB minus MB. Again, CB minus MB is CM. So CM equals to CB, that is B, minus MB, that is X. So CM in total equals to B minus X. So I write it down here that CM or MC equals to B minus X. In the next step, I will present to you rule number 2. We will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. So whenever you draw from a common external point two tangents to a circle, then the lengths of those two tangents must be equal to each other. In this case, PA equals to PB. So we actually can implement rule number 2 in our drawing. Why? Because in our drawing, we have the common external point A. From the common external point A, we have two tangents to this circle, tangent AN. We define the point of tendency of tangent AC with this circle as point S. So from the coming standpoint, point A, we have two tangents to this circle, tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AN equals to AS. But AN is A minus X, therefore AS must be also equal to A minus X, according to rule number 2. Likewise, we'll focus on the coming standpoint, point C. From the coming standpoint, point C, we have two tangents to this circle. Tangent tangent CS and tangent CM, and according to rule number 2, they are equal to each other. That is to say, CM equals to CS, but CM is B minus X, therefore CS must be also equal to B minus X. CS equals to B minus X. According to our definition, the length of the hypotenuse AC is C from one side, but from one side, AC equals to AS plus SC. Again, AC equals to AS plus SC. So C equals to AS, that is A minus X, plus SC, that is B minus X. So in total, C equals to A minus X plus B minus X. That is to say, C equals to A plus B, minus X is minus 2X. So in total, C equals to A plus B minus 2X. Here we add 2x to this equation, and finally we get that C plus 2x equals to A plus B. Here we subtract C from this equation, and we get that 2x equals to A plus B minus C. Here we divide this equation by 2, and finally we get that x equals to A plus B minus C over 2. So here we developed a formula that will help us to find out the radius of a circle that is blocked by a right triangle only by knowing the side lengths of the triangle, of the right triangle that blocks this circle. That is to say, the radius x of this circle that is blocked by the right triangle ABC must be equal to A plus B minus C over 2. Now we can implement the new formula in our drawing. Why? Because in our drawing, we have the right triangle ABC blocks this circle. So we will define the radius of this circle that is blocked by the right triangle ABC as R. So according to the new formula, the radius R of this circle that is blocked by the right triangle ABC must be equal to AB plus BC minus AC over 2. I repeat again, the radius of this circle R that is blocked by the right triangle ABC, according to the new formula, must be equal to R equals to AB plus BC minus AC over 2. Okay? So we get that the radius R equals to AB that is 7 plus BC that is 24 minus AC that is 25 over 2. 7 plus 24 is 31. 31 minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of this circle R that is blocked by the right triangle ABC, it is equal to 3 units in its length. Likewise, we find out the radius of this circle that is blocked by the right triangle ABC according to the same formula. We'll define the radius of this circle as x. So the radius x of this circle that is blocked by the right triangle CDA must be equal, according to the new formula, it must be equal to CD plus DA minus CA over 2. Repeat again, the radius of this circle that is blocked by the right triangle CDA must be equal to x equals to CD plus DA minus CA over 2. CD is 7 plus DA that is 24 minus CA that is 25 over 2. 7 plus 24 is 31. 31 minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius x equals to 3 units. Here x equals to 3 units in its length. X equals to 3 units. So those two circles have the same on the eye. We define the point of tendency of tangent BC with this circle as point M. So the radius PM that is equal to 3 units is drawn to point M, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. If BC is perpendicular to NP, it means that this angle equals to 90 degrees. And this angle will be also equal to 90 degrees according to rule number 1. In the next step, we will define the point of tendency of tangent AB with this circle as N. And we will join points P and N together by straight line. Pn is the radius of this circle that is equal to 3 units. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. That is to say, this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to rule number 1. So inside quadrilateral NPBM we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral NPBM we have 4 right angles, therefore we can relate to this quadrilateral NPBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say NP equals to BM. But NP is 3, therefore BM must be also equal to 3 units in its length. So likewise, according to the same rule, in rectangle NP BM, side PM must be equal to side NB, but PM is 3, therefore NB must be also equal to 3 units in its length. So I actually found out that quadrilateral NPBM is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square is equal to 3 units. Okay, so we actually can repeat on the same process here, and we get that the quadrilateral that we create here according to rule number 1 will be also square. So we define the point of tendency of tangent AD with this circle as point T. This angle will be equal to 90 degrees according to rule number 1. We define the point of tendency of tangent DC with this circle as L. We join points Q and L together by a straight line. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Inside quadrilateral LQ dt we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, can relate to this quadrilateral LQ dt is a rectangle. We know that the opposite sides of a rectangle are equal to each other. Here QL is the radius of this rectangle that is equal to 3 units. The opposite sides of rectangle QL dd are equal to each other. That is to say LQ equals to dt, but LQ is 3, therefore dt also must be equal to 3 units in its length. Likewise, in the same rectangle QTLD, QT equals to LD, but QT is 3, therefore LD must be also equal to 3 units in its length. Again, we found out that quadrilateral LQ dt is a rectangle. Inside a quadrilateral LQ dt is a square. Each side of this square is equal to 3 units in its length. In the next step, we will extend the radius TQ of this circle by a straight line until it touches side BC of the rectangle. the radius of any circle is a straight line, and when you extend a straight line by straight line, the result is a straight line. We define the point of tendency of the extended TQ, of the extended TQ and BC as point Z. As I already mentioned here, TZ is one straight line. By extending the radius TQ, we create a quadrangle QC dt. In this quadrangle QC dt, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So inside quadrangle ZC dt, we have 4 right angles. Therefore, we can relate to this big quadrangle ZC dt as a rectangle. And you also know that the opposite sides of a rectangle are equal to each other. That is to say, dt equals to ZC, but dt is 3. Therefore, ZC must be also equal to 3 units in its length. Likewise, in the same rectangle, DC equals to TZ. But DC is 7, therefore TZ must be also equal to 7 units in its length. Alright, the TZ, this side TZ of the rectangle equals to 7 units in its length. In the next step, we will extend the radius NP of this circle by a straight line until it touches side DC of this rectangle. And we define the touching point of the extended radius NP inside DC of the rectangle as point Y. Again, when you extend the straight line by straight line, the result is a straight line. Therefore, NY is a straight line. In this way, by extending the radius NP, we create a quadrangle NBCY. In this quadrangle NBCY, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside quadrangle, the big quadrangle NBCY, we have 4 right angles. Therefore, we can relate to this quadrangle NBCY as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NB equals to side YC. But NB is 3, therefore YC must be also equal to 3 units in its length. Likewise, according to the same rule, in the same rectangle NYBC, side BC must be equal to side NY. But BC is 24, therefore NY must be also equal to 24 units in its length. And I think that NY equals to 24 units in its length. This side NY equals to 24 units in its length. We define the intersection point here as point K. So inside the small quadrilateral KYZC, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. So we can relate to this small quadrilateral KYZC as a rectangle. Why? Because we have here 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, YC equals to KZ. But YC is 3, therefore KZ must be also equal to 3 units in its length. Likewise, in the same small rectangle, side ZC must be equal to side KY. But ZC is 3, therefore KY must be also equal to 3 units in its length. We have already found out that TZ equals to 7 units. So TZ, that is 7, minus KZ, that is 3, minus zt that is also free must be equal to the missing side, side kq. I will remind you that we extended the radius tz by a straight line and the result is tz. When you extend the straight line by a straight line, therefore, when you extend the straight line by a straight line, the result is a straight line. So tz is one straight line. So I found out that the missing side, side kq, is equals to tz minus kz minus zt. So the missing side kq equals to tz that is 7, minus kz that is 3, minus zt that is also 3. So kq equals to 7 minus 3 minus 3, that is 1. So we found out that the missing side here, side qk equals to 1 unit in its length. Likewise, we'll find out the length of the missing side, line segment pk. Because of the fact that when we extended the radius np by straight line, we got ny. When you extend the straight line by straight line, the result is a straight line. So ny is one straight line. So ny minus np minus ky equals to the missing side pk. So write it down. Ny minus np minus minus ky equals to the missing side pk. I'll repeat again. The missing side pk equals to ny minus np minus ky. So the missing side pk must be equal to ny that is 24 minus np that is 3 minus ky that is 3. So in total pk equals to 24 minus 3 minus 3, that is actually 24 minus 6, that is 18. So we found out that the missing side here, side pk equals to 18 units in its length. Yeah, the missing side, side pk equals to 18 units in its length. I repeat again that tz is one straight line. So we'll focus on this side of the straight line tz at point q. Here, the sum of the angles on this side of tz at point q must be equal to 180 degrees. So which angles we have at this side of tz at point q? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees, according to the rule that the sum of the angles from one side of a straight line is equal to 180 degrees. So the missing side here, the missing angle here must be equal to 90 degrees. So this angle equals to 90 degrees. Likewise, DC is one side of rectangle ABCD, therefore it is absolutely a straight line. DC is one side of a rectangle ABCD, it is absolutely a straight line. So we know that this angle equals to 90 degrees and this angle equals to 90 degrees. So if we focus on this side of the straight line DC at point Y, here the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at this side of DC at point Y? We have this angle that is equal to 90 degrees, plus the missing angle. In total they must be equal to 180 degrees, therefore the missing angle here must be equal to 90 degrees. So inside quadrangle Q, inside this quadrangle QLYK, inside this quadrangle we have 1, 2, 3 right angles. Therefore the fourth angle here must be equal to 90 degrees. This angle equals to 90 degrees. We'll focus on the upper side of the straight line NY at point K. Which angles we have at the upper side of NY at point K? We have this angle that is equal to 90 degrees, plus the missing angle. In total they must be equal to 180 degrees according to the rule that I mentioned. Therefore the missing angle must be equal to 90 degrees. And therefore triangle QPK is the right triangle. Why? Because this angle equals to 90 degrees. In the next step we will implement the Pythagoras theorem on the right triangle triangle QPK. So I'll copy the right triangle QPK in a new page, and we implement in this right triangle QPK the Pythagoras theorem. Okay. By PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QPK that I copied from the original domain. QK equals to 1 unit in itself, PK equals to 18 units in itself. By PT is the version for Pythagoras theorem. According to the Pythagoras theorem in this right triangle, QP squared, that is the square of the hypotenuse, must be equal to QK squared plus PK squared. So QP squared equals to QK squared. QK is 1, therefore QK squared is 1 squared, that is 1, plus PK squared. PK is 18, therefore PK squared is 18 squared, that is 324. So QP squared in total equals to 324 plus 1 is 325. QP squared equals to 325. We will take a root out of this equation, and we will get that QP equals to the square root of 325. But 325 is 25 times 13. And we will take 25 out of the root. So the square root of 25 is 5. Inside the root we left only with 13. In conclusion, we found out that QP, that is to say, the distance between the centers of those two circles, that is actually the length of this line segment QP, is equals to either 5 times square root of 13 units, so in terms of numbers, it is equals to 18.03 units. I repeat again, the radius, the distance between the centers of those two circles QP equals to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. In the next step, I will summarize the lecture. We start here. So we have in the drawing rectangle ABCD. We know that side AB of this rectangle equals to 7 units. The length of this rectangle AD is 24 units. Inside this rectangle, we have those two circles. The center of this circle is there at point Q. The center of the circle is there at point P. Our mission is to find out the distance between the centers of those two circles, that is to say the length of this line segment QP. So because of the fact that ABCD is a rectangle, it means that all those 4 angles are right angles, and you also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC, but AB is 7, therefore DC must be also equal to 7 units in its length. Likewise, according to the same rule, side AD equals to side BC, but BC is 24, therefore AD must be also equal to 24 units in its length. Then we focus on the right triangle ABC, and we implemented on this right triangle ABC the Pythagoras theorem. According to the Pythagoras theorem, in the right triangle ABC, AC squared equals to AB squared plus BC squared. Repeat again. In the right triangle ABC, by PT is the abbreviation for Pythagoras theorem, AC squared equals to AB squared plus BC squared. So AC squared equals to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC is 24, therefore BC squared is 24, that is 576. So in total, AC squared equals to 49 plus 576, that is 625. So AC squared equals to 625. We took out of this equation, we found out that AC equals to the square root of 625, that is actually 25. So the length of the hypotenuse AC on the right triangle ABC, AC equals to 25 units in its length. So here we have the right triangle ABC is blocks this circle, and the right triangle ADC blocks this circle. So in the next step we develop a special formula that will help us to find out the radius of any circle that is blocked by a right triangle. We will find out the radius of the circle only by knowing the side lengths of the right triangle that blocks the circle. So here we have the right triangle ABC. This is the right triangle because this angle ABC equals to 90 degrees. The right triangle ABC blocks this circle, and according to our definition, the radius of this circle is x. We define the point of tendency of tangent BC with this circle as M. OM is the radius of the circle that is equal to x according to our definition. The radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO according to rule number 1. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees. Likewise, we define the point of tendency of tangent AB with this circle's N. We join points O and N together by set line. ON is the radius of this circle that is equal to x. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AN will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral NOBM, we have 1, 2 right angles, therefore the fourth angle must be equal to 90 degrees. So this quadrilateral has 4 right angles, therefore can relate to quadrilateral ONBM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say NO equals to BM. But NO is x, therefore BM must be also equal to x. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. But OM is x, therefore NB must be also equal to x. So actually found out that quadrilateral NOBM is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other, each side of this square is equal to x. So what is the length of line segment AN? From the drawing it is very easy to see that AN equals to AB minus NB. That is to say AN equals to AB, that is A, minus NB, that is x. So in total AN equals to A minus x. Then we found out the length of this line segment CM. From the drawing it is very easy to see that CM equals to CB minus BM. Again, CM equals to CB minus MB. So CM equals to CB, that is B, minus MB, that is x. So in total CM equals to B minus x. So in conclusion we found out that CM equals to B minus x and AN equals to A minus x. Then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. We have the common standpoint point P. From the common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, whenever you draw two tangents from a common standpoint, then the lengths of those two tangents must be equal to each other. In this case, PA equals to PB. We can implement rule number 2 in our drawing. Why? Because in our drawing, if you focus on the common standpoint point A, from the common standpoint point A, we have two tangents to the circle, tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AN equals to AS. But AN is A minus x, therefore AS must be also equal to A minus x. Likewise, according to the same rule, if we focus on the common standpoint point C, from the common standpoint point C, we have two tangents to the circle, tangent CM and tangent CS. And according to rule number 2, they are equal to each other. That is to say, CM equals to CS. But CM is B minus x, therefore CS must be also equal to B minus x. So in total, I found out that AS equals to A minus x and AC equals to B minus x. AC is the hypotenuse of the right triangle ABC, and according to our definition, AC equals to C. But AC also equals to AS plus SC. So we can write here that C equals to AS plus SC. AS is A minus x and BX is B minus x. So in total, C equals to A minus x plus B minus x. That is to say, C equals to a plus b minus x is 2 minus 2x, so in total c equals to a plus b minus 2x. We added 2x to this equation, and finally found out that c plus 2x equals to a plus b. We subtracted c from this equation and found out that 2x equals to a plus b minus c. Then we divided this equation by 2 and finally found out that x equals to a plus b minus c over 2. So actually developed a formula that will give us the radius of a circle that is blocked by a right triangle. We'll find out the radius of any circle that is blocked by a right triangle only by knowing the side lengths of the right triangle that blocks the circle. That is to say, the radius x of this circle that is blocked by the right triangle ABC must be equal to a plus b minus c over 2. Now we can implement the new formula in order to find out the radius of this circle that is blocked by the right triangle ABC. We define the radius of this circle as R. According to the new formula, R must be equal to AB plus BC minus AC over 2. I'll repeat again, the radius R of this circle that is blocked by the right triangle ABC must be equal to AB plus BC minus AC over 2. AB is 7, BC is 24, minus AC is 25 over 2. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of this circle R that is blocked by the right triangle ABC equals to 3 units in its length. Likewise, we found out the radius of this circle that is blocked by the right triangle ADC. According to the new formula, we get that the radius of this circle that is x must be equal to CD plus DA minus CA over 2. Repeat again, the radius of this circle x that is blocked by the right triangle CDA must be equal to CD plus DA minus CA over 2 according to the new formula. CD is 7, DA is 24, minus CA that is 25 over 2. 7 plus 24 is 31, and 31 minus 25 is 6, and 6 over 2 is 3. So finally found out that the radius of this circle x also equals to 3 units in its length. Then implemented rule number 1 in this circle. We define the point of tendency of tangent BC with this circle as M. The radius PM is drawn to point M, therefore according to rule number 1, this circle equals to 90 degrees and this circle also equals to 90 degrees. Likewise, we define the point of tendency of tangent AB with this circle as N. The radius Pn is drawn to point N, therefore according to rule number 1, this circle equals to 90 degrees and this circle equals to 90 degrees. So inside the quadrilateral Pn, BM, we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees. So inside quadrilateral Pn, BM, we have 4 angles, therefore can relate to this quadrilateral Pn, BM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say Pn equals to MB, but Pn is 3, therefore MB must be also equal to 3. Likewise, according to the sum rule, PM must be equal to MB, but PM is 3, therefore MB must be also equal to 3. So we actually found out that quadrilateral PN, BM is not a rectangle but a square, while because all of its sides are equal to each other, inside of this square is equal to 3 units. Likewise, if we implement rule number 1 in this circle, we'll get that LQ dt is also a square. Each side of this square also equals to 3 units in its length. Therefore, found out that those two squares are identical. Okay. In the next step, we extended the radius TQ of this circle by side line until it touches side BC of the rectangle at point Z. When you extend the straight line by straight line, the result is a straight line, so TZ is one straight line. Inside quadrilateral TDZC, we have 1, 2, 3 rectangles, therefore the fourth angle must be equal to 90 degrees. So inside quadrilateral TDZC, we have 4 rectangles, and therefore can relate to this big quadrilateral TDZC as a rectangle. And we also know that the opposite sides of the rectangle are equal to each other. That is to say dt equals to ZC, but dt is 3, therefore ZC must be also equal to 3 units in its length. According to the sum rule, TZ equals to DC. but DC is 7, therefore TZ must be also equal to 7 units in its length. Here TZ equals to 7 units in its length. In the next step, we extended the radius NP by a straight line until it touches side DC at point Y. In this way, we created quadrilateral NBYC. In this quadrilateral NBYC, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. Therefore, inside quadrilateral NBYC, we have 4 right angles, therefore can relate to this quadrilateral NBYC as a rectangle. And we also know that the opposite sides of rectangle are equal to each other. That is to say, NB equals to YC, but NB is 3, therefore YC must be also equal to 3 units in its length. Likewise, according to the sum rule, side BC of the rectangle must be equal to side NY, but BC is 24, therefore NY must be also equal to 24 units in its length. Here, we wrote down that NY equals to 24 units in its length. In the next step, we defined the point of the intersection point here is K, and we focused on the small quadrilateral KYZC. Inside this small quadrilateral, we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees. Therefore, quadrilateral NYZC that has 4 angles, we can relate to this quadrilateral as a rectangle. So in rectangle KYZC, the opposite sides are equal to each other. That is to say, KY equals to ZC. But the ZC is 3, therefore KY must be also equal to 3 units in its length. According to the sum rule, in rectangle KZCY, KZ equals to YC. But YC is 3, therefore KZ must be also equal to 3 units in its length. Okay? I repeat again that we extended the radius TQ by straight line, and in this way we got the straight line TZ. So TZ is one straight line, and we already found out that TZ equals to 7 units in its length. So TZ that is 7, minus TQ that is 3, minus KZ that is also 3, must be equal to the missing side, side QK. I'll repeat again. The missing side, side KQ, must be equal to TZ minus KZ minus ZT. Okay? Here, again, KQ equals to TZ minus KZ minus ZT minus ZT. Okay, so KQ equals to TZ that is 7 minus KZ that is 3 minus ZT that is also 3. So in total KQ equals to 7 minus 3 minus 3 that is 1. So we found out that the missing side here, side QK equals to 1 unit in its length. We found out that NZ and NY is one straight line that is equal to 24 units here. So NY that is 24 minus NP that is 3 minus KY that is also 3 must be equal to the missing side, side PK. Again, NY minus NP minus KY equals to the missing side, side PK. Repeat again. The missing side, side PK equals to NY minus NP minus KY. So the missing side PK equals to NY that is 24 minus NP that is 3 minus KY that is 3 also. So PK equals to, in total, to 24 minus 6, that is 18. So we found out that the missing side here, side PK equals to 18 units in itself, and we already found out that QK equals to 1 unit in its length. Then we focused on, we have the straight line TZ. If we focus on this side of the straight line TZ at point Q, here the sum of the angles must be equal to 180 degrees according to the rule. Then the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have this side of the straight line TZ at point Q? We have this angle that is equal to 90 degrees, plus the missing angle in total, they must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing side and the missing angle must be equal to 90 degrees. We have already found out that this angle equals to 90 degrees. In the next step, we focused on this side of the straight line DC at point Y. Here, the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at this side of DC at point Y? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees. So we should found out that inside quadrangle QLYK, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. This angle equals to 90 degrees. Then we focus on the upper side of the straight line NY at point K. Which angles we have at the upper side of the straight line NY at point K? We have this angle that is equal to 90 degrees. Plus the missing angle. In total, they must be equal to 180 degrees. So the missing angle here must be equal to 90 degrees. And because of the fact that angle QKP equals to 90 degrees, it means that the green triangle QKP is a right angle. So I copied the green right triangle QKP in a new page and we implemented this green right triangle QKP, the Pythagoras theorem. This is the right triangle KQP that I copied from the original drawing. KQ equals to 1 unit in its length, PK equals to 18 units in its length, and this angle equals to 90 degrees. According to the Pythagoras theorem, in this right triangle PQK, PQ square equals to QK square plus PK square. So PQ square equals to PK square. PK is 1, therefore PQ square is 1 square, that is 1, plus PK square. PK is 18, therefore PK square is 18 square, that is 324. So in conclusion, found out that QP square, that is the square of the hypotenuse, equals to 1 plus 324, that is 325. So QP square equals to 325. We took a root out of this equation and finally found out that QP equals to the square root of 325. But 325 is 25 times 13. We can take 25 out of the root. The square root of 25 is 5. So inside the root, we're left only with 13. In conclusion, we found out that the length of line segment QP, that is the distance between the centers of those two circles, it is equal to either 5 times square root of 13 units, so in terms of numbers, it is equal to 18.03 units. So repeat again, the distance between the centers of those two circles, that is to say the length of line segment QP equals to either 5 times square root of 13 units, so in terms of numbers, QP equals to 18.03 units. Okay, thank you very much.